Welcome back. In the last couple of classes, we discussed varieties of NMR parameters like chemical shifts, scalar coupling, coupling strengths, and multiplicity pattern. And also, I introduced to you the Popper nomenclature where strong and weak coupling spins can be defined by the Roman alphabets of this. For example, two weakly coupled spin system, if it is there, we refer to as AX spin system. If it is strongly coupled, we denote it as AB. Similarly, for more coupled spin system like 3 or 4, we represented them by different Popper nomenclature. And also we discuss about what happens to the Popper nomenclature when there are chemically equivalent nuclei, when there are more spins present, groups of equivalent spins present, like CH2 group, CH3 group, etc. How to represent them by Popper nomenclature. And we took one or two examples of analysis of such spectra like AX, AB, A2, AMX, and quickly we saw some of the analysis of the spectra of AA prime AX, AX2, etc. Like this, there are a lot of things we can discuss, a lot of spin systems can be analyzed. In fact, that itself can be a subject of discussion by itself. Okay, so what I will do is I will continue today with the real analysis of the 1H NMR spectra with typical examples. Now, moment I say 1H NMR, what can I get from that? Supposing I have a molecule like this. If I take a proton NMR spectrum, I can get the information about the chemical shifts of all these protons, their coupling interactions, etc. So I will be getting more information about proton structure of this molecule, proton positions, who are the nearest neighbors, etc. I can do. If I want to get the carbon-13 skeleton or carbon-13 information of this molecule, I have to do say carbon-13 NMR. So if I take carbon-13 NMR, I will know, I'll get information about these carbons in this molecule. If you also see carefully, this molecule also has a nitrogen. I can take nitrogen 15 NMR and get information about the nitrogen present in the system. Although you can look at it very carefully, there is one more NMR active nuclei like this, O70. This also can be studied if one is interested. Then we can get information of the oxygen 70% in this molecule. So essentially, depending upon the molecule of your interest and the type of NMR active nuclei present, how many different NMR active nuclei that are present, you can study that type of NMR spectrum, start the analysis by assignment of the peaks, getting the structural information. First you get spectral information like chemical shift, coupling constant, etc. And I will tell you as we go ahead later, you can use this information to get the structure, conformation, dynamics of these molecules. Now I am going to take, as far as the analysis is concerned, the first order spectrum with some representative examples. Some of them are representative. Okay. First, of course, I analyzed a family tree approach. We discussed this at the end of the scalar coupling, where it was applicable to weakly coupled spin system. We are looking at this proton CH, which is coupled to two other protons. We discussed this problem and we understood, we generated the multiplicity pattern for this proton. Okay, let us say this proton is coupled to two other protons, CH, one with a coupling of 8 Hertz, other with a coupling strength of 5 Hertz, and also to a CH2 group with a coupling strength of 6 Hertz. Remember, exactly the same problem was discussed and we generated the multiplicity pattern. CH proton splits into a doublet because of this CH, one of the CHs, and it is each of them split further into a doublet because of another CH, and each lines of this doublet of doublet splits into a triplet because of coupling to CH2 group. Essentially, the spectrum as far as CH group is concerned, the multiplicity pattern is like doublet of doublets of triplets. Of course, in a given molecule, I took example for this. Of course, you can also take the example for the multiplicity pattern, how it comes for CH2 group, how it comes for this CH, etc. You can work out all those things later. So right now, I don't think that is a matter of too much of importance for us because this already we have learned. Now we'll go into the analysis of. Okay, let us look at now the analysis of proton and carbon 13 spectrum of a simple molecule like CH2D2. Now with the knowledge we have gained in last few classes, we have discussed a lot of things. You must be in a position to analyze this spectrum of this molecule. I don't give you the spectrum. We can generate the spectrum. We can find out what type of spectrum we should expect for this molecule. I am now looking at proton spectrum H2 of this molecule. But I'll also give you information. Deuterium is spin 1 and carbon 13 is natural abundance is 1%, that is spin half. This information is sufficient for us to generate the spectrum for proton spectrum of this molecule and also carbon 13 spectrum. Okay, we are studying this molecule, the natural abundance of carbon 13. Remember, it is not a label system. Carbon 13 is in its natural abundance and we are trying to analyze the spectrum. Let us get the proton spectrum. This information is given. Now there are three types of couplings possible in this molecule. There are three different NMR active nuclei: carbon 13, proton and deuterium. There can be CH coupling, there can be HD coupling, there can be CD coupling. All the three are possible. All are one bond couplings. Of course, HD is this also should be 1D. Okay. Now let us look at the proton spectrum of this. Proton experiences coupling with the deuterium. We are not bothered about carbon 13, as you know. Why? Because in natural abundance is 1%. We look at major compound, major isotope number, carbon 12 attached. Carbon 12 has magnetic moment 0, this one. So that will not couple to proton. Now how many peaks I expect for proton? Remember, this proton will be coupling to deuterium. What is deuterium spin? Spin 1. Use the same familiarity approach. To this one, this deuterium, two deuteriums which are magnetically equivalent, will split this proton or these two protons because of J coupling. Now, if you put 2Na plus 1, what I am going to get is, put 2, there are two nuclei here, 2 into 2, spin of deuterium is 1 plus 1, so it is totally you are going to get 5 lines pattern. But what is the intensity pattern? Of course, you can work out very easily. Like there is a Pascal triangle which I gave for spin half nuclei. There is also a Pascal triangle for spin 1 nuclei, spin 3/2 nuclei, etc. Now, without going into that, I will tell you the intensity pattern of this proton split because of this two deuterium, equivalent deuterium will be 1, 2, 3, 2, 1 multiplied. Of course, carbon 13, as I said, 1%, it will not split. Okay, that is the spectrum of proton coupled to deuterium. Now, I will look for the carbon 13 spectrum. What type of spectrum we are going to get for carbon? Of course, we discuss more about carbon NMR in the next 1 or 2 classes in depth. I'll tell you a lot about carbon 13 NMR. At the moment, let us consider that we know something about, similar to analysis of proton spectrum, we can generate carbon 13 NMR spectrum just by looking at the splitting patterns. When you look for the carbon 13 NMR, remember, you are not now worried about Isotopomer. You are directly looking at carbon 13 isotopomer. When I am looking for proton, you have to look at, you have to say that there are 92%, 99% of the molecule with carbon 12 and 1% of the molecule with carbon 13 isotopomer. But now you are directly looking at carbon 13. It is like there is no question of looking for acetylates and all those things, like I said earlier. So what are you going to get here? The carbon 13 is split by proton, two equivalent protons. It will become a triplet. Again, remember 2Na plus 1 rule apply. This direct detection of carbon 13, though in natural abundance, is split by carbon proton 2 into a triplet. This we have observed already. So it is going to be a triplet. But now deuterium is also coupled. We are like, this is not simply sitting here. That will couple to this. Then what is going to happen? Each line of this split carbon 13 triplet is split into 5 lines by deuterium. Why it splits 5 lines? I told you in the previous example of proton. Like it split proton into 5 lines. These two equivalent deuterium also split carbon 13 into 5 line pattern. So how many lines you are going to get? You get triplet for carbon due to proton coupling, and each line of this triplet is split into a pentet like of 1:2:3:1 intensity. So you will get 15 lines for carbon 13. One group of lines, 1:2:3:1 line, and then another one, another one. But remind you, the central peak has double the intensity because carbon 13 is split by 1:2:1 triplet by proton. The pattern remains same, but each line of this triplet is further split by 5 lines. That's all. So totally you are going to get 15 lines for this carbon 13 spectrum. Very interesting, right? It's a simple molecule, remember. Now I can also ask a question. What happens if I see deuterium? Let us take the example. I looked at the proton spectrum. I looked at the carbon 13 spectrum. Now I'm going to look at deuterium spectrum. What do I get? Now carbon 13 is in natural abundance here. Assume that abundance is small and it is not going to split this deuterium. So what are we going to get? This is split by two equivalent protons into a triplet. It will become a triplet. That's all. Okay, it will become a triplet. Now all the three nuclei we can study here, and we can generate the multiplicities pattern. This is how we can analyze spectrum of even a small molecule with several nuclei present. Okay. Now we will start with a simple example. This is a very famous spectrum which you will see in most of the textbooks. What could be the spectrum of this? What could be the molecule which gives a spectrum like this? If I ask this question by giving the spectrum, look at it. You have a triplet, you have a quartet, and a singlet. Common sense tells me this triplet, when it is coming of equal intensity of 1:2:1, I will say this must be attached to a CH2 group. As a consequence, CH2 splits this peak, this proton, whatever it is, into a triplet. Similarly, when I say there is a quartet of intensity 1:3:1, this proton must be attached to a CH2, CH3, which splits this proton into a quartet. You understand? This is split into a triplet because of CH2. This is split into a quartet because of CH3. This is a proton which is not split by any other protons. It is giving rise to a singlet. So you can find out the intensity also tells me this intensity, this is the integral intensity values. This intensity is 1, 2, and 3. This also tells me the number of protons present in this group is 1, Number of protons present in this group is 2. Number of protons present in this group is 3. Am I right? It is true. But I am not telling it is absolute number. It could be more. It could be multiples. For example, 2, 4, 6. That's also allowed. It ratio of the multiplicity of these three groups of peaks are 1:2:3. You consider like that. Consider the ratio of this proton to this proton to this proton is 1:2:3. Because this can be CH2, this can be some 4 protons, this can be 6 protons. It's possible. Now, what is the first guess for this molecule for this type of spectrum? Of course, CH3CH2OH. You can think of that, where CH3 is split into a triplet because of CH2. CH2 is split into a quadrat because of CH3. OH is not split by either of them. That's what we expect, right? So it is quite likely this could be the spectrum of ethyl alcohol. I have not given you the molecular formula or not molecular structure also. Let us see. Now, molecular formula is not C2H5OH, it is C5H12O2. Spectrum looks identical to ethyl alcohol spectrum, but the molecular formula is different. So, your analysis is correct. There is a CH3 group, there is a CH2 group, and some uncoupled proton. Need not be OH, it could be CH or something is there. So, how do you now tell me what is the structure of this molecule? So, one thing in this case, I'll give you the structure. This is the structure of molecule. Look at the structure. Now, there is a perfect symmetry along this axis. So, this is CH3 group, this is CH3 group, this is CH2, this is CH2, and this is CH2. Now, this CH3 is a terminal CH3. This and this are identical. There is a chemical equivalence. That is because of symmetry. So, essentially, molecule has only 3 groups of protons. 1, 2, and 3. That's all. So, this one, now there is a coupling between them. There is a single chemical bond. There is one bond here. Because of that, this CH3 is split into a triplet because of the CH2. Correct. It is understandable. And this CH2 is split into a quadrat because of the CH3. That's correct. What about this CH2? It is separated by 2 or 3 bonds. It is not experiencing coupling with this CH2 or this CH3. So the CH2 uncoupled to any of these groups gives a single peak. But now intensity ratio is 1:2:3. Now if I take this proton as number 2, there are 2 protons. This is 2 plus 2, 4 protons. This is 3 plus 3, 6 protons. It agrees with the intensity ratio. It is 1:2:3. This is not a single proton, but it is CH2 protons. In which case, the uncoupled CH2, then you can get the intensity ratio perfectly as 1:2:3. So you could analyze the spectrum and you can interpret it for a particular molecule if you know the formula and if you know its structure also. So it's very easy to interpret. This is for CH2 group, that one. Now, similar spectrum is there. I'll give you another molecule and molecular formula is also given. C3H6PCl2, Cl2, C3H6Cl2. Now tell me, how do we interpret the spectrum? Remember, just carefully look at the spectrum. This is a triplet. This is 1, 2, 3, 4, 5. 5-length pattern is a pentate. Remember, I told you, when do we get the pentate? When we interpreted the multiplicity pattern under scalar couplings. That's why I introduced lots of multiplicity pattern for you, so that looking at the spectrum, you know what it is. So we get a multiplicity pattern. It is a pentate here. And there is one group which is a triplet. But again, intensity ratio is 1:2:3. Interesting. This also looks like a ethyl alcohol spectrum, but unfortunately, it is not ethyl alcohol because the formula given is different. Now, how do you understand this? This is 1 proton, 2 protons, and 3 protons. And this is the formula. If you write, see what is happening here. This is CH3 group. This CH3 is split into a triplet because of CH2 here. Two equivalent protons are present here, CH2 group. This will split this CH3 into a triplet, correct? And there are 3 protons, terminal CH3, intensity is 3. What about this one? This is CH2 group. It is coupled to CH3. As a consequence, it will split this CH2 into a quartet. Use the 2Ni plus 1 rule. It is a quartet, 1331 quartet. But that is not all. This CH2 is also coupled to the CH proton. What does it mean? What will happen now? If you look at this quartet, each line of this quartet is further split into a doublet because of the CH proton. So what will happen? You are not going to get only 4 lines, a quartet of intensity 1331. You are going to get 8 lines. Okay? 8 lines in such a way, 1331 ratio is still maintained. A doublet, doublet, and a doublet of intensity 1:1, 3:3, 3:3, 3:2, and again 1:1. But in reality, it is going to be overlap. It is not distinctly different coupling, because couplings, if they are very much different, you would have got that distinctly different pattern. A small doublet, a big doublet, and a small doublet of same ratio 1:3:1. But now there is a overlap of peaks. As a consequence, a quartet, each line of the quartet split into a doublet which will overlap and gives a pentate pattern. Please recollect what I said about the pentate, multiplicity pattern. So it is a pentate pattern. What about this CH? This CH is experiencing coupling with CH2. What will happen then? It will become a triplet. But now intensity ratio agrees. This is 1 proton, this CH. This is 2 proton, CH2. This is CH3, 3 protons here. So intensity ratio agrees. Multiplicity pattern also agrees. You know how to interpret. Sometimes very simple molecule. So it can be complicated. When you look at the spectrum, you will be wondering, what is the CH2 coming? Then immediately you say it is attached to CH2. Then what is this pentate? You must understand immediately. This must be a proton coupled to 2 types of protons. That's how you should start the analysis. I hope you agree with me. You all are with me, huh? Now I'll take this molecule, another molecule. Formula is also given. C4H8O2. Again, triplet, quartet, and a singlet. But now the intensity ratios are different. This is 3, 2, 3. One first conclusion you can draw looking at the spectrum is there must be CH3 coupled to CH2, like in the previous example. So it is a triplet. Then this is CH2 is coupled to CH3, so it must be a quartet. Then what about this one? Why it is 3 peak, 3 intensity is 3, and also no splitting here? Let us see the molecular formula now. This is the molecular formula. Very interesting, right? Now this is a CH3 protons. This CH3 group is split by CH2 into a triplet. This is split into a quartet because of this CH3. So these two are understandable. Now immediately look at this intensity, and also it comes downfield in the chemical shift. This is far away coming downfield. Then you must understand 3 protons, if they are present in a single line, it must be a CH3 group. You should have, and that too without splitting. Only one peak of the intensity 3 without any splitting means it must be a CH3 group. But since it is coming to the downfield, you must think it is attached to a electronegative group, and generally methoxy groups come in this region. As a consequence, you can immediately say It is a OCH3 group. So this is the very easily you can interpret the spectrum. This is CH3 group, this is CH2, and this must be OCH3. Simple spectrum, we should know now how to interpret. Okay, we can interpret this one also. Now we will not go into this. This also we will not go into this. Okay, let us take this molecule. Something interesting is there here. Now I am giving you the molecular formula. It is C5H10O2. And the spectrum is very simple. Look at the spectrum, very simple. There is one CH3 group or whatever it is, one single peak of intensity 3. There is one group of multiplicity with intensity 3. There is one multiplet with intensity 2 and one singlet with intensity 2. Now, we have to generate the molecular structure for this. You have to get a structure and then make the assignment of the peaks. As usual, CH3 and CH2 must be there. That is the first guess because it is a triplet and this is a quartet. So this must be CH2 and this must be CH3. Intensity ratio agrees 2:3. But how do you account for a single peak with 3 and 2 intensity? Are we in the right track? We do not know. Let us look at this structure now. Very interesting again. What is happening here? This is a terminal proton, terminal CH3 here. And it is coupled to CH2 here. As a consequence, this is a triplet and this CH2 is a quartet. So intensity ratio also perfectly agrees. And if you look at this molecule, we have a CH2 group here, which is in between this and this, separated by O here and double bond O. And these two protons, the CH2 protons, do not experience any coupling with this group or this group. So what happens? It remains a singlet and it is CH2 protons. As a consequence, it gives a singlet of intensity 2. So this can be accounted for CH2 protons. As I said in the previous case, there is a OCH3 group. It is not OCH3, C double bond OCH3 is there. This CH3 is not coupled to anything and remains a singlet of intensity 3. Very clear, right? So analysis becomes very simple. Now you make this as proton 2 assignment. I have numbered the protons here. You can assign the peaks with the same numbering. This is a proton 1 uncoupled and do not couple to anything. And this is proton 2, do not couple to anything. This is proton 3, the CH2 coupled to CH3. This is CH3 coupled to CH2. As a consequence, there is a multiplicity. So, very simple analysis. This is where we can go ahead and start analyzing the spectrum very easily. Now, why this proton 2 has moved to downfield? This is one important question we can answer. Because we have discussed a lot about chemical shift. When it is attached to electronegative atom, what happens and everything. Remember, proton 2 is moved downfield because it is allylic proton and also has attached to electronegative oxygen through carbon. As a consequence, this proton moves very much downfield. Now, this is a spectrum taken from book of Pavia, 4th edition. Let us see how do we interpret this spectrum. Okay, this molecule is 1-chlorobutane. That is, chlorine is attached to one position. Now, as a consequence, what happens? There is no symmetry here. If it was Ca3, then there would have been symmetry in this molecule. Now, just because you knocked off one proton and attached chlorine, symmetry is broken. Now, how many groups of protons are present here? There are 4 different groups of protons here. CH3, CH2, CH2, CH2. And I remember I took the example when there is an electronegative atom is attached, how the chemical shift moves. The one which is directly attached to the electronegative atom, This withdraws electrons here. As a consequence, this gets de-shielded. I told you. So this has to come to downfield. Look at the spectrum. There is only one group of protons, one group of peaks, which is coming downfield. This triplet must be for the CH2. Of course, this CH2 protons comes here. Why it is a triplet? You can look at the molecule now. It is attached to CH2. As a consequence, this proton D has to be a triplet. Correct? Very well. We understood. This is a triplet. So this is attached. Now what is the next one? Remember, the terminal CH3 is easy to attach. Easy to you make the assignment. Look at the CH3 here. Always CH3 comes in the high field region. This CH3, because it is coming here, look at the intensity is given here. This is nearly 3 intensity. So this must be CH3 peak. Looking at the intensity also, we can say the CH3 peak. Further, why it is a triplet? Because it is attached to proton B, which is CH2. So CH2 splits the CH3 into a triplet. Very clear. Now we have to understand B and C. This is slightly tricky. Please understand. I don't have to explain. Looking at the pattern, we should say which is B and C. Both are 2 intensity, right? Both are 2 intensity. If I don't tell you which is B and B, look at the multiplicity pattern, you can say. You know why? Look at this proton B. This proton B experiences couplings with CH3 group and CH2 groups. What will happen then? This CH2 will become a quartet because of CH3. Right? 1:3:3:1 intensity quartet. But each line of the quartet is split into a triplet because of the CH2 protons. In both the cases, you have to apply 2ni+1 rule. So what will happen? 1:3:3:1 quartet, each line of the quartet is split into a triplet. What did I say for this one? It is quartet of triplets. Depending upon the coupling strength, which coupling is larger. If this coupling is larger, it is triplets of a quartet. So it depends, whatever you want. That we do not know the coupling. But in the interesting situation, what happens here is, as a consequence of several overlaps here, look at this pattern here. This is more complex than the other one. This must be the proton attached to CH3 and CH2. Very easily you can assign this to B. Look at this group now. This group of multiplicity. This also has proton 2 intensity wise. This must be what? Now you have assigned this, you assign this, you assign this. Then this must be the one left over. True. But then what is the multiplicity? Why it is coming? Remember, this CH2 experiences coupling with this CH2 and also this CH2. So what is the pattern? Because of coupling with this CH2, it is a triplet. And each line of the triplet is split further into a triplet because of this CH2. As a consequence, you see, some of the lines are overlapping, you get a pentate. This is what we observe, we generate the pentate pattern, you know. Remember, when I was explaining the multiplicity, I generated sextate, pentate, septate, various things I generated. This is the reason I use that. I spent extensive time on that to make you people understand. So now you can look at it. This has to be this CH2, this one, which is split into triplet of triplets. This is quartet of triplets. This is a triplet as a triplet. So intensity clearly agrees. 2 intensity, 2 intensity, 2 intensity, and 3 intensity. Very nicely you can interpret the spectrum. You can also use your knowledge of chemical shift with electronegative substituent. You say this comes down and CH3 comes up. Only confusion was between CH2s, which is which, that you look at the multiplicity pattern. Very simple molecule. You see so much of information you can get. You can use knowledge of chemical shift. CH3 comes here and CH2 attached to the proton comes downfield. And the multiplicity pattern and intensity pattern you can utilize, area of the peak. And also, for assigning B and C, use the pattern you get. That is pentate, that is more complex, depending upon whether it's how the splitting arises, how the multiplicity comes because of coupling with neighbors, you can even make the assignment. So all the information which I gave you about chemical sheets, coupling, multiplicity pattern, everything can be utilized here to analyze the spectrum. The simple molecule I gave you, you are able to analyze. I hope what I am going to do is, I will stop with this analysis today. We'll come back tomorrow and continue with the interpretation of more complex molecules. In next one class or two class, I'll spend more time in analysis so that you get a feel for analysis. Finally, you will get a molecule of your interest, you synthesize in chemistry lab, come back and take the spectrum of an unknown molecule. Okay, the molecule structure is known, spectrum is known, you can interpret. But you must be in a position to analyze, interpret the spectrum of an unknown molecule which is synthesized. So we have to know how to interpret the spectrum and get the structure. So we'll try to get into more and more analysis, couple of more spectra in the next one or two classes.